It's an enormous pleasure to welcome this afternoon Tim Palmer. Tim is an old personal friend of mine, which is lovely to see, and also one of the world's most distinguished meteorologists and climate modelers. Tim did a PhD in Oxford on relativity, and then moved from that to working in meteorology at a number of places, including the UK Met Office, the European Centre for Medium Range Weather Forecasting, and then came back to Oxford about 15 years ago, wasn't it? With a 12 or 13, with a hugely prestigious Royal Society research chair, which he still occupies, and he's professor in climate physics in our Department of Physics here. Tim, we're going to talk about climate change, but I want to ask you a few questions about yourself, first of all. How did a student in relativity end up in meteorology?
Pretty much by chance, I would say. You know, I did as you say, did a PhD in relativity, where I was focusing on something which is actually quite topical today, but at the time was a bit of a niche thing, which is how do you define the energy of a gravitational wave, of these kind of ripples in space-time when, I don't know, neutron stars collide or get sucked up by black holes. And there are some kind of conceptual problems about what that means. Anyway, I came up with a possible solution, and then had to sort of, I mean, I got offered a position actually in Stephen Hawking's group in Cambridge to carry that on. But I started to have kind of, not exactly cold feet, but sort of started to think, well, how many people in the world are really, really, really interested in what I'm doing? And I sort of sat down with a pencil and paper and came up with about 6 people. And I thought, is this really what I want to spend the rest of my life doing? As I say, as it happens, we now can detect gravitational waves, so perhaps, you know, what I do now did then might be more relevant today. But I then started sort of looking around at other potential fields, and I met a sort of renowned climatologist by chance. And the curious thing was he talked about a thing called the principle of maximum entropy production as a kind of guiding principle in climate, or potentially guiding principle in climate. And only a few weeks before, my own supervisor had been trying to persuade me that the principle of maximum entropy production should be a guiding principle in understanding how black holes work. And I'd never heard of this principle of maximum. I've never been taught it at university, you know, I had to kind of read it up. And I thought, that's interesting, you know, the same idea kind of seems to connect climate and black holes. Maybe trying out climate for a few years to see what it's like would be worth it. So, yeah, I managed to persuade the Met Office interview board because they'd never heard of the principle of maximum entropy reduction, but I told them this was the most important principle that you'd understand everything about weather and climate, and I kind of bludgeoned them almost into accepting me and giving me a position. So in the end, that worked out pretty well.
So again, we're going to be talking largely about climate, but could you just say a little bit about your work on weather forecasting, and in particular the Ensemble approach that you led,
right,
and now sort of dominates the weather forecast we get on television?
Well, I mean, the one thing I really brought from my relativity work was the fact that the world, on the whole, is quite a non-linear system. You know, things interact, I suppose one could say, at a very non-technical level, but relativity, the general relativity, is a non-linear theory, and climate is very non-linear. And of course, you know, one of the things that underpins weather is chaos theory, which is almost the kind of epitome of non-linear systems. And Ed Lorenz is the founding father figure of, he's an MIT meteorologist, wrote this paper in 1963. And I think everybody knows, you know, had heard of the butterfly effect, that, you know, if we don't have a precise knowledge of the initial condition for some forecast, it could be weather or it could be the economy, it could be any kind of forecast, potentially in a nonlinear system that error or uncertainty can grow. And that was kind of understood, but as I sort of dug more and more into these nonlinear systems, I began to realize this notion of the butterfly effect is not something fixed. It's not like, you know, a week or so into a forecast, the butterflies start kicking in and making the forecast unreliable. The very fact that we're dealing with nonlinear systems means that this growth of error is actually dependent on the starting conditions. Some initial conditions can be very, very predictable for long periods of time, and other initial conditions can be very unpredictable almost immediately. So it's like you have this potential super butterfly effect, but it only kicks in intermittently. And I sort of argued with my colleagues that this is a potential problem for weather prediction, to know when the super butterfly effect will be kicking in. And the only way to really know that ahead of time is to, run multiple versions of your model with small perturbations.
That's what's called the ensemble.
And that's what we call an ensemble. And I think, certainly a lot of my colleagues, it's not so much they were skeptical, but they thought this wasn't the best use of computer time. Be better off refining processes and adding more detail into the models. But Mother Nature kind of helped in the sense of the famous October '87 storm, which you and I are old enough to remember, and perhaps not necessarily everyone here. But this was the mother of all lousy forecasts on the TV, where the meteorologist, Michael Fish, his name became quite famous for a sort of failed forecasting system. Andy Haldane, the chief economist at the Bank of England, when the 2008 crash happened, the financial crash, he called that the Bank of England's Michael Fish moment. So actually, this super butterfly effect probably also affects things like economics and pandemics and all sorts of nonlinear systems. But anyway, that was a great example because it was completely misforecast. And we were able to show retrospectively this was actually a case where small uncertainties, it grew explosively fast over just a period of a day or so. But they could be picked up ahead of time by an ensemble system.
So if it was to happen today, the weather forecast wouldn't be someone phoned up to say there'd be a hurricane. It would be there is a small probability of a very nasty
There is a probability. You may, those of you who have weather apps on your iPhone will always see probability of precipitation. You may curse, why can't they say things more precisely? But you can probably blame me for that to some extent. But there is a more serious point here, which is that I think one of the really important applications of this technology, if you like, is for disaster risk management. And, in the past, it's always been a frustration that a hurricane hits somewhere or a tropical cyclone, and all the agencies go in after the event trying to distribute food and medicine and so on. And of course, all the communications are down, the roads are down, everything's down. So it takes forever to get this aid to people who are who have suffered. They haven't really been, because they've got limited funds, they haven't been able to just send out supplies ahead of time when they're not really sure whether the forecast is good or not. What a probabilistic forecast does is give them an objective decision theoretic method of deciding when to take precautionary or I think it's called now anticipatory action to send medicines and food. So ensembles, so what they do is they analyze the costs and losses, cost benefits and everything and say, okay, when the probability of one of these severe, say, tropical cyclones exceeds, let's say 60%, 70%, whatever they decide is the right thing, then they send in the medicines and the food and so on ahead of time. So this has really become quite I would say, a sea change in the way in which these aid agencies operate. And I think having ensemble forecasting has allowed that to be cast in an objective, framework and I think it's been a very positive.
And we both know from conversations we've jointly had with the Foreign Commonwealth and Development Office just how interested they are in that.
Yeah, it's affecting pretty much all these agencies around the world. So this is a really good development.
Tim, just before we go on to climate change, I want to give you an impossible task because I know you've not completely given up fundamental physics.
Right.
And that I think you once told me that you have essentially a theory of everything that Penrose can't prove is wrong or things. Can you, in a couple of sentences, say what your idea is there?
Probably not.
Or give us a
But by the
flavour.
way, I should say Roger Penrose was a sort of teacher of mine during my PhD days, and he was my internal PhD examiner and a very influential person. And probably some of my views have been, have resulted from interacting with Roger, who's an extraordinary person in many different ways. And one of those is that quantum mechanics, for all its fantastic successes, may start to fail in the regime where gravity starts to become important. And this was the holy grail when I was doing my PhD. How do you combine quantum mechanics and general relativity together to make we have the so-called standard model of particle physics, which unifies electromagnetism and the nuclear forces. But people have tried for 70 years or more to push gravity into that framework and can't do it. And Roger has been saying for some time that actually maybe the problem is quantum mechanics is wrong.
Which is a linear theory.
Which is a linear theory in a sense, that's right, whereas general relativity is a very nonlinear theory. So, Einstein's great insight was geometry. Let me just say it, so 2 sentences. Einstein's great insight was that geometry is a guiding principle in physics. Chaos theory actually also ultimately is about a type of geometry in what's called the state space of systems, and it's a fractal geometry. So what I've been trying to do is try to understand, is there a role for fractal geometry at a very deep fundamental level in physics, and in particular in formulating quantum mechanics in a way which, let's say, is more appealing to general relativity. And I would say there are some possible hints that that might be an idea, but it's so far off the left field that most mainstream, probably particle physicists wouldn't give me much time of day. But it's something.
That was a brilliant flavour of the theory, and we perhaps should get you back to talk about it in greater depth. But let's go on to climate change. And I guess I wanted to start with the real basics. So why is it that when we put CO2 and a couple of other gases into the atmosphere that we get warming?
The first thing to say, of course, is that the basic physics of climate change is actually 19th century physics. It's not what we would say, it's not rocket science, let's say, although, it's interesting science. But it's stuff that was, goes back a long time. And it's ultimately to do with the fact that the sun radiates energy at, visible and ultraviolet light. The Earth receives that energy and it radiates it back in infrared, with infrared light, infrared photons, which is kind of heat energy. And certain gases in the atmosphere, carbon dioxide being one, water vapor being another, can trap that energy. So when we calculate, what is the temperature of the Earth, it's a kind of a balance. It's the balance between the energy coming in from the sun and the balance of the infrared energy going out. Now, if we increase the amount of carbon dioxide in the atmosphere from our emissions of burning fossil fuels, obviously we're increasing that kind of blanket of carbon dioxide. Now, at some level, there is a slight subtlety here that the way I sometimes explain it is to imagine that you're in outer space looking down at the Earth with infrared goggles. You wouldn't actually see the surface of the Earth for this kind of obscuring carbon dioxide. So you would be seeing a level in the atmosphere a few kilometers above the surface, typically. So you wouldn't see the surface at all. Now imagine, you increase carbon dioxide, you double it, let's say. So there's now more carbon dioxide. What actually happens is you will start to see photons emitted because the blanket now extends out a bit more. You'll start to see photons that are a little bit higher up in the atmosphere than previously. Now, as you go up in the atmosphere, at least in what's called the troposphere, the temperature decreases. So if nothing else happened, this increase in carbon dioxide would cause an imbalance because you'd be radiating from a colder part of the atmosphere, so there wouldn't be as much infrared going out. So now the energy coming from the sun would exceed the amount of energy going out. So the atmosphere achieves that rebalance by warming up. And it warms up. As it warms up, then it radiates more infrared, and you get to an equilibrium where the temperature is warmer. And that warming extends from that level where the atmosphere is, where the CO2 is emitting, down to the surface by sort of convective motions and fluid turbulence and all that sort of stuff. So that's basically, that is what the greenhouse effect is. So our carbon dioxide levels will warm. Now, the problem with that explanation is that if that was the only thing going on, climate change would not be the kind of potentially disastrous, catastrophic thing that we believe it to be, because a pure sort of doubling of carbon dioxide would only warm the atmosphere by a degree or so. So what makes it a difficult problem is that there are additional factors which amplify that signal. And a good and not terribly difficult one to understand is the role of water vapor. Yeah. So as I mentioned, water vapor, so it's the gaseous form of water, is itself also a greenhouse gas. And again, that was understood by John Tyndall in the 19th century. But as you warm the atmosphere from CO2, you evaporate more water into the air from the oceans, so the atmosphere becomes moister. And we see that very clearly from observations as the temperature has risen, so the average humidity in the air has risen. And so that's giving you an extra boost, yes, if you like, to the greenhouse effect, which might bring it up to 2 degrees now from 1 degree. And then, and that's pretty clear, but then there is a big uncertainty, which is what happens when the water vapor condenses into clouds, because clouds are exceptionally complicated things on a kind of global scale. Low-level cloud, I don't know, sort of stuff that's around today and probably most of the time in Oxford. Low-level cloud tends to radiate the sun. It scatters light from the sun back into space, and actually ends up cooling the atmosphere, cooling the surface. Whereas if you have cloud at a much higher level, that can actually be what's called cirrus type of clouds, so the more wispy ice crystal clouds. That actually plays more of a role in trapping heat from the surface. So in a sense, whether climate change will be a catastrophe for humanity or not is going to depend critically on how clouds respond to CO2. And we don't understand that terribly well.
So Tim, if we park clouds, if one's allowed to say that for a moment, and then perhaps come back to it. But as I understand it, then some of the basics around climate change have been understood since the days of Tyndall and Arrhenius, yes, in the 19th century. But of course, as you've just said, there are complex feedbacks and interactions. Right. And we want to know how much and where the warming occurs. And that's why we need the climate models. And I wonder if you could walk us through the development of climate models in the second half of the 20th century, and in particular, the role of the two scientists who got the Nobel Prize last year.
Yes, we were very happy, of course, and I never thought I'd live to see the day, actually, when climate science would be recognized, yes, as part of mainstream physics, which of course it is. But I mean, Suki Manabe, who I know pretty well from Princeton, apparently, I mean, the story apparently goes that when he was phoned up by the Swedish Academy, he says, "You must have the wrong person. I'm not a physicist, I'm a climatologist." I said, "Well, no, Professor Manabe, you are a physicist." So he developed the first sort of three-dimensional climate model. They pretty much developed from...
And when you say three-dimensional, that's dividing the atmosphere into blocks, both spatially and then going upwards.
Exactly, yes. I mean, treating the whole globe, the separate latitudes and longitudes, and then going up into the stratosphere. And I'll say a bit about that in a second. But the models are kind of offshoots of weather forecasting models. So weather forecasting, computational weather forecasting started pretty much straight after the Second World War. John von Neumann at Princeton got some of the leading meteorologists to code up weather type equations on the then ENIAC computer, big valve computer. And that worked pretty well. And then people started asking the question, well, could we kind of simulate the climate of the Earth? You know, the fact we have deserts and monsoons and cyclones and, you know, low pressure systems, high pressure systems, just from first principles, you know, just start the atmosphere off at rest and let it go. And does it produce all this stuff? And Princeton pretty much took the lead in that area. And Manabe came to Princeton from Japan in the 60s. And he was the one really to start saying, well, we could use these models to understand how, I don't know if people called it climate change in those days, but how our potential burning of fossil fuels, you see, people already realized in the 60s that this could be a problem in the future. And he said, well, we could work this out in our models. And he did the first, you know, serious attempt to describe the three-dimensional sort of structure. And it's worth just saying two things. What his model showed, this is back in the sort of late 60s, early 70s, so two very important things. One is that the Arctic would be a kind of hotspot for warming. It would be a place where warming would be especially large, which has definitely turned out to be the case. And the other thing he showed was that whilst the lower atmosphere warmed under climate change, the upper atmosphere would actually cool. And he made the point that this is going to be an important test of deciding in the future whether what we see is due to human emissions of carbon dioxide, or, for example, could be due to the fact the sun's output was changing. Because if the sun's output was changing, it would just warm up everything. And in fact, this is what we have seen, that what we call the troposphere, the lower 10 or so kilometers, 15 kilometers, the atmosphere is warming, but the stratosphere above it is cooling. So it's exactly what Manabe had predicted. People that say that climate models haven't predicted anything, it's complete bunk, you know. These are two very serious and important predictions. Hasselman sort of, I mean, what I've called this warming below, cooling above is what you might call a fingerprint of climate change. And Hasselman took that whole kind of technique further to talk about the different types of patterns that you would associate with climate change rather than, say, natural climate variability. But climate models are becoming more and more important because people want to know more than just, is the global temperature increasing? They want to know what it means for, you know, their countries or their regions, obviously for adaptation purposes. But actually, even for mitigation, I mean, maybe we'll talk about this later, but you know, there are questions like, are we going to pass tipping points? Because that will determine how quickly we need to act. Because once you pass a tipping point, you can't reverse it. That's the definition of a tipping point. So models are really our only a reliable way of answering that sort of question.
So if one thinks of the sort of last 30 years of, or longer than that, 50 years of climate modeling, then, as you said, there are some non-intuitive phenomena that the models have explained. If you were to sort of go to the other end and say, what are the areas where climate change models, at least as they exist at the moment, are least successful in explaining or predicting or informing us?
What are they least successful?
Least, yes.
Well, unfortunately, it's things like, for a particular region of the world, that's, you know, take a country in Africa, for example, as just, you know, or, you know, somewhere South America. You're kind of faced with a kind of, suppose you were saying, well, what infrastructure, if you're, you know, prime minister or whatever it is of that country, you've got to spend money on adaptation. But then the question is, what actually are you adapting to? Because on the one hand, you might have, okay, it might get hotter, it might get drier, it might have more droughts and heat waves, and potentially, you know, forest fires and things like that. Or the type of weather that might dominate the future climate of your country might be stormy weather, you know, intense flooding, potentially storm surges and things like that. So, you know, that would imply a whole different type of adaptation strategy, you know, towards bigger storm sewers and flood defenses and things like that. And so unless you have the models and you can rely on the models, it's really difficult to know sometimes what are the key issues that we actually should be focusing on in climate adaptation.
So simplistically, is that just a question of resolution? I mean, perhaps you might say something about the grid size or the cube size and how that's evolved from the early work to the state of the art today. And is it just a question of you need to be able to model at...
Well, to some extent, you know, unlike, you know, we're talking about quantum gravity as a very sort of esoteric topic just now, where we sort of don't really know even what the equations are that we're wanting to solve. I mean, that's the challenge. What actually are the right equations? Here for climate change, we think we understand what these equations are because they're sort of most of it's 19th century physics. There's a bit of quantum mechanics.
These are the famous Navier-Stokes equations.
An example is Navier-Stokes, named after the French churchman Claude Navier and Irish physicist George Stokes, which are basically Newton's laws of motion applied to a fluid like, you know, a glass of water or the air in the atmosphere. So they're pretty, you know, you write them down, they're understood, there's nothing ill-defined about the equations. But because they're nonlinear, they're exceptionally difficult to solve. And the sort of desire to increase the resolution of these climate models, in a way, is that the primary reason for doing it is that it means that we're solving these equations more accurately. The problem is, you see, if you have a very coarse, I mean, the idea is you break up the Earth into a kind of checkerboard, you know, and then you imagine, I mean, you do this because you're giving the computer the job of solving the equation. And what the computer then is given is a kind of pseudo atmosphere where everything within one of the boxes of your checkerboard or draftsboard or something, spherical draftsboard, is uniform. So you make this kind of ad hoc assumption, everything within that grid box is uniform. Everything is mixed up. You know, the air has got a single temperature, a single humidity, a single wind speed, and then you calculate everything. But that introduces errors. It means you're not solving these nonlinear equations accurately. And the only way to reduce that error, it's kind of numerical analysis 101, if you like, is to reduce the...
And just give us a flavor of how big these grid squares were and then now are today.
Well, I mean, one thing I should, so if you go into for example, the latest IPCC report, most climate models are around, the grid boxes are around 100 to 150 kilometers square.
So that's still a big assumption, that one's assuming that within that quite big area, it's homogeneous.
Yes, I mean, that itself the problem is not so much that assumption per se, but what the implications of that assumption are. And because energy, you know, can propagate upscale, if you make an error in those grid boxes, does that start to affect the accuracy of your simulation on much larger scales? And on all the evidence is that it does. It does affect the accuracy of your simulation on the larger scale. I should say, by the way, that you know, we have very good evidence in numerical weather prediction where you don't make forecasts out to 100 years, but out to, you know, a week or two into the future, that as the resolution of the weather forecast models has decreased, I mean, because back in the 70s, they also had 100 kilometer resolution, and now they're around 10 kilometers resolution, the global models. And as that has happened over the years, the accuracy of forecasts has improved. So we've got pretty clear evidence that, you know, the more accurately you solve the Navier-Stokes equations, the better forecasts you get. And there's every reason to suspect that'll be true for climate as well. The problem with climate is, you know, you don't have the same level of verification data as you do with weather forecasting. Every day you're kind of testing your model with a new weather forecast.
So what does that mean for science policy going ahead in looking about how to get better resolution, better?
Well, look, I think the most important thing to say is, you know, the current generation of models is clearly demonstrating the threat or the risk of serious climate change. So I'm not, I don't want people to misunderstand what I'm saying. We have enough evidence now to know about the risk of, 4 degrees of warming by, early in the next century or something like that. I mean, if some of these cloud feedbacks are positive, which they probably are, but we're not certain, that's not unreasonable. And if you want to know what 4 degrees of warming means, Mark Linus wrote a wonderful book a few years ago, where he each chapter was, what does 1 degree look like? What does 2 degrees look like? What does 3 degrees?
He actually talked about it at the Martin School.
Okay. I mean, 4 degrees is a vision of absolute hell. I mean, nobody would want to live in a world like that for 100 different reasons. So the models are quite clear. There's a kind of a serious threat that this may happen if we don't urgently cut our emissions. So we don't need better models to refine that. Where we need them is, as I say, where it's important to, I mean, there are a number of reasons, but to get more regional detail for adaptation, perhaps to, as I say, to be a bit clearer about what, things like these tipping points, which could completely negate the effect of what's called negative emissions. Sucking CO2 out of the air in 50 years' time, when we've passed the tipping point, won't return us back to where we are now. So that's an important point. And there are also sort of things to do. I mean, something that bothers me a bit actually is our the UK's energy policy, which is very much predicated on, Boris, I think, said, so we'll be the Saudi Arabia of wind power in the future. And that's fine if the wind carries on blowing, but we don't actually understand that well how, particularly at a regional level, how winds will respond to climate change. And last year was a good example of where the winds across the North Sea actually didn't blow very much, and the amount of renewable wind energy was much less. It was about a third, I think, less than expected.
So conceivably, that might be something that happens more often.
That might certainly be something that happens more often, but the IPCC class models completely disagree about this. Some say yes, some say no. It's like a complete, we just don't understand, and we can't model the processes. The processes associated with these anticyclonic, they're called blocking anticyclones, where you get persistent anticyclonic weather, are very complex, very nonlinear. There's some evidence that the melting of the Arctic might actually have an impact on that, because that's reducing the equator to pole temperature gradient, and these anticyclones do depend critically on that equator to pole temperature gradient. But broadly, we don't understand. That's the sort of thing we don't understand. So, that's another example of something feeding into kind of mitigation policy. And then the last thing to say, perhaps, is, people talk about a plan B, which is geoengineering. Could we spray sulfates, aerosols into the stratosphere to block the sun? The problem with that is that we're solving a problem in the infrared, the greenhouse effect, by changing the solar input in the visible and ultraviolet. And we don't really understand what that might do to the hydrological cycle of the Earth. And would we really do that if we didn't know, for example, that we're going to start messing around with the monsoons or start shutting off moisture supply into the rainforests? So again, it's sort of inconceivable that we do anything like this without a decent scientific base. And I don't think the current models give us enough confidence that we understand that type of process well enough.
So there is a clear need for better models that won't tell us it's not going to be a get out of jail card. We don't have to worry about climate change anymore, but they are going to help us.
Well, they might do. I mean, it's not completely get out of jail, but if it's not inconceivable. And I say sometimes this to climate skeptics who don't like climate models. I say, well, it's not inconceivable. It may tell us that actually this cloud feedback really is negative. So clouds are going to save us. It's going to stop us warming more than, 1.5 degrees.
And you say conceivably, but if you put your hand on your heart, you'd say low probability.
I think it's a low probability,
Yeah.
but you know, I mean, I try to be a sort of
Optimist.
neutral, dispassionate scientist, and it's not. But the only way we're going to find out is to invest in the science to understand those processes better.
So just going on to investing in the science, then I guess one component of that is having models which are just more powerful, running on bigger computers. And then the second component is having more sophisticated algorithms that give you a bigger bang for your buck, if you say, if you will. Is that fair? And if so,
well, I just wanted not to jump over the bigger computers for a second, because it's a frustration to me that we tend to, I mean, we have big computers in the world. Most of the big computers, really big computers, are actually used for simulating weapons, nuclear bombs and things like that. So climate scientists typically have to go to, you know, general purpose supercomputers and get 10% of some machine. And I find that pretty unsatisfactory. So I've long been an advocate of, you know, dedicated, I mean, we're coming very close to what's called the era of exascale computing.
I can never remember my powers of 10. What is exa?
Yeah, so 10, peta is 50, sorry, getting me confused now. Peta is 15, is that right? And exa is 18, or is
18,
it?
is it?
Or is it 15? Oh, gee.
Sorry, I shouldn't have asked a consolidated question. A big number, whatever.
10 to the 15, I think 10 to the 15 floating point operations per second will be feasible within the next 2 years. So a group of us are sort of trying to make the case that we need dedicated exascale computing for climate, and that will allow these kilometer scale models, kilometer being the scale that we're looking towards simulating. But your question about AI,
I mean, just before getting onto that, I mean, very roughly, what scale of resources would be required for a dedicated exascale climate model?
Well,
in billions of dollars.
Well, an annual budget of, it's not a big deal, you see. It's an annual budget of around maybe 1 to 200 million a year.
So that's very small.
Yeah, it's tiny.
Yeah.
I mean, compare it to what we spend on, I mean, CERN, we spend billions a year. We just sent this telescope off to Lagrangian point. That cost billions and billions.
But that's the running cost, and the initial capital cost of the computer?
Well, yeah, the initial cost would be in the tens of millions, but you know, the running, I mean, electricity of course has to come from renewable energy, but you know, electricity costs, and then, you know, manpower and stuff, but we're talking about 1 to 200 million.
So a naive question, why hasn't that happened? Because it seems...
It's a complicated question. I think that if we were starting from scratch, it would have happened. But when you have labs which have their own sort of vested interests, and there's a bit of politics in it, because, I mean, it's a little bit like CERN. You know, in the early days of CERN, certain universities in the UK, for example, weren't desperately keen on CERN because they thought it would, you know, it would put their own labs' preeminence in question. And there's a bit of that. In Europe, we kind of suffer a bit from the fact that we don't have a very strong supercomputer industry. So it's not, you know, unlike the European Space Agency, a lot of the projects, you know, it's quite clear. I mean, they fund science, but they're also funding jobs in the aerospace industry. And Europe, putting a lot of money into supercomputing doesn't necessarily translate into a lot of jobs. We'd be maybe buying a machine from America or Japan or somewhere.
I mean, are you optimistic? Do you think it's just a matter of time before the need for this?
Yeah, well, I'm actually I'm optimistic in the sense that actually the European Union has started a big project towards a billion, literally a billion, it will be close to €1 billion project on developing the next generation kilometer scale model. And there's a consortium in Europe called EuroHPC, Euro High Performance Computing, that are putting in the computing resources. The bad news for us in the UK is that all of this is funded under what's called Digital Europe, and we're going to have no ability to to play an active role. It's a direct consequence and a rather disastrous consequence, in my view, of Brexit. But I'm optimistic in that sense that I think it is happening and it will happen. But we in the UK need to find ways in which we can kind of keep active collaboration with our partners around the world. And I think that will need some dedicated funding from the UK government.
We're going to go to your questions in a second, but I have one final question for you before we do this, and you alluded to it. I know you've been working on improving the algorithms, getting bigger bangs for your computing buck, and the application of AI and other machine learning techniques. Yes. Might you say a little bit about what that is and the prospects?
Yeah, I mean, this has come about because, you know, in the past, there was a thing called Moore's Law, which meant that you only had to wait, you know, a year and a half or so, and you get a new computer that was twice as big as the one before. So I think people got, I don't want to be too critical of my colleagues, but perhaps got a little bit sloppy about worrying about computational efficiency, because they always knew, well, a bigger computer will be coming along, so, you know, why put a lot of effort into it? But, you know, transistors have shrunk down now to atomic scale, so we're not going to continue to double the speed of computers every 2 years. So looking for ways to make these codes run more efficiently, make better use, if you like, of the computing resources, is now an important area. And it's not one I had envisaged myself working on, because I thought this was much too engineering and sort of not really my thing. But it turns out, actually, there are some really interesting and deep scientific problems in designing efficient code. It's not just an engineering problem. It's quite sort of, I could talk a lot about this, but I don't have time. But it raises a lot of really interesting and deep kind of mathematical questions, which I found quite fascinating. But so AI is a great, there's a role for AI, not least because the numerics of AI are just matrix multiplications, and that's really, really, really fast on computers. So the more we can use that type of technology, the better. The other thing which AI has done has spawned the growth in what are called low precision CPUs or GPUs. And if people know, I mean, if you don't know what I'm talking about, it doesn't matter. But traditionally in scientific computation, numbers have been represented by 64 bits. That's been the kind of default. Going down to there weren't actually physically computers that could run 16-bit arithmetic efficiently. But now with AI, there are these 16 or even 8-bit chips available. And that's really another really interesting area of trying to figure out which parts of a climate model you can run with 16-bit numerics rather than 64-bit numerics without degrading performance. Because that means you get that 4 times or even potentially more than 4 times speed up.
And I said we'd park clouds, but clouds and storm formation are some of the things you might be able to represent.
Yeah, exactly. That's the whole point about a kilometer scale model. You can start to now represent kind of thunderstorm clouds. And thunderstorm clouds are absolutely 100% central to understanding the circulations in the tropics and things like the El Nino events and monsoons and all these big things that happen in the tropics. And these are critical for climate change. How's El Nino going to change? How are monsoons going to change? So being able to resolve down to cloud scales and thunderstorm cloud scales will really make us quantum change in our ability to simulate climate.
Okay, we're going to go to questions, and I'm going to alternate between online and in the room. And for people in the room, if you could wait for Clara to come with the microphone. But let me start, and I should say that if you're online, do ask a question or feel free to vote on questions, because I'll try and do the most popular ones. So I'm going to start off with online, and the most popular one is from Franz Baumann. Tim, which tipping points are you most concerned about?
Well, there are a number of tipping points to think about. One is the famous, what's called the thermohaline circulation, this big oceanic circulation. People sometimes call it the Gulf Stream shutting off, which is actually not accurate, but it's a big circulation in the atmosphere. And there's pretty clear evidence that it's linked to for example, I talked about monsoons. The African monsoon is linked to the strength of the thermohaline circulation. So we might be casting a lot of for example, sub-Saharan Africa into permanent drought if there was a tipping point in the thermal haline circulation. The other big ones, of course, are things like the disintegration of ice sheets. So if we start warming Greenland and the Antarctic too much, the loss of ice might not just be from melting, but actually physical disintegration. And the other one, which I think was reported on very recently in Nature, was the rainforests. That, I mean, it's a combination of our own, mankind's sort of degradation of the rainforest by agriculture and so on, but also the fact that climate change may lead not only to warming, but to a drying, sort of a shutting off of the moisture supply. So which am I most worried about? Geez. I mean, the ice sheets are really serious because that can lead to really serious sea level rise around the world, meters of sea level rise, if you're talking about a sort of a major disintegration of some.
I think the rainforest Amazonia one scares me because that could happen over a couple of decades, whereas the ice sheets could take, the worst things is going to be a century.
Well, we don't know. Again, I would say we don't know. I mean, I wouldn't be confident in relying on models of the cryosphere to have a clear idea about timescales.
Right, questions. We have one at the front here.
Thank you very much for that fascinating talk. Two quick questions. What would happen if the West Antarctic ice sheet were to collapse and fall in? What would the implications around the world? And number two is, what are your thoughts on integrated assessment models and how they're informing policy? Just if you can share your thoughts on those two, that would be great. Thank you.
Well, I'm going to pick up the second question first, if you don't mind, because that is something which bothers me a lot. Integrated assessment models typically take very, very coarse-grained information from climate models to make, for example, economic assessments. I mean, I think Nick Stern has been quite kind of critical about, the level of detail in some of these economic models. But equally, I would say that the information that these models use from the climate sphere is also very, very kind of limited. We talked about having these exascale computers. I really would like to see, I mean, I'm kind of getting quite a big, having done some reading about it over the last year, quite a big fan of things like agent-based models to try to represent economic units at a regional scale. And I see it entirely plausible in the future that one can form a global picture of climate impacts on different sectors of the economy, not through these very kind of coarse-grained integrated assessment models, but actually integrating models at the regional scale around the globe. I think this is quite an exciting kind of area for bringing scientists from different domains together. I suppose, I mean, as I say, the loss of ice, land ice, is a problem for mainly because of sea level rise. And the fact that such a large fraction of our society lives close to sea, close to the coast. And so they're at threat from that. If we're talking several meters, then there's no alternative than to relocate somewhere, and that's obviously a big problem for society.
So let me ask you one from the web. This is from Troy Fielder. What challenges do you encounter when attempting to communicate your models to the public or policymakers? And please don't say fatuous interview questions.
Actually, very interesting, because you said the public or policymakers. I find the two groups to be completely different in the way they respond. When I talk about uncertainties to the public, I mean, I think they get it. When I say we can reduce the uncertainties with an investment of a couple of $100 million a year, as not just the UK, but on a sort of international scale, they get it. They say, in fact, they say, it's a bit like you. They say, well, it's such a small amount of money. Why haven't we done it? When you talk to policymakers, I don't know, they kind of want to believe, I think, that the science of climate change is all done and dusted. And when you tell them, no, actually, there are still big uncertainties, it's kind of like that's an unwelcome message. It sort of interferes with their big sort of vision they have about climate change. So I have no problem, I have had no problem, as far as I'm aware, communicating with the public. But I've had a lot of trouble trying to convince policymakers that there really are important, I mean, in societally, policy-related important questions where we need continued, in fact, we need an enhanced scientific investment. Now, you know, I suppose their reaction is, oh, well, he would say that. He's a climate scientist, so it's just more toys for the boys sort of thing. But I think that's a kind of a silly attitude to have, because we're talking about a serious problem here. I mean, I can go away and do my quantum mechanics, and I'd be happy to do that. But I think climate change is an important problem, and we're kind of going into the future like with fuzzy glasses, and we could do so much better by going to Specsavers and getting some proper glasses.
Thank you. Let's have another one from the audience. Just wait for the, thank you.
Thank you. My name's Hugh Lee. How much energy do your models use in computational, in such big computers? And different related question, you were talking about the atmosphere. Presumably your models also model the oceans at the same time, and the grid covers the depth as well. But do they cover things like the melting of the permafrost and the related release of methane, which then is going to change the atmosphere and change the climate?
Yeah, so the first question is, sadly, I mean, it's kind of a consequence of Moore's law, or the failure of Moore's law, that the way computers have developed over the last supercomputers over the last few years is by basically them getting bigger and bigger. There are more of these cabinets with more processors and things like that. And that's made them more energy profligate, if you like. And probably an exascale computer would be, I don't know, 20, 30 megawatts or something like that. These are not insignificant. And that's why it is vital, obviously, for doing this work. You know, they have to be sited in places where there is plentiful renewable energy. And another thing, by the way, is, of course, you know, half of that energy is used to, you know, move data around in the computer. Almost half of the energy is used to cool the computer. So if you can have it in a place which is naturally cool, such as in Scandinavia or somewhere like that, that's a good thing. So where these supercomputers will be in the future, those issues, you know, availability of renewable energy and you know, relatively cool conditions are going to be important. Yeah, I mean, current models they certainly include the oceans, but they try to represent things like you talked about, the permafrost and the methane class rates under the permafrost and the potential release of methane. That's obviously another amplifier that I talked about.
And just relating to a question from Garth Wilkinson, that's got a few votes, then it also includes carbon sequestration by plants and things.
Yes, that's right.
Yeah.
That's the sort of thing actually where AI can play a role, because you know you can't model obviously every plant, so you have to do that in a kind of bulk formula way, and representing that type of a process with the type of neural nets that AI sort of typify an AI system is actually a really kind of fast, numerically fast way of doing that calculation.
So I think we have time for two questions, one from the web and one here. One from the web, but from Robert Chris, that I'm going to slightly abbreviate. So hopefully we'll get to net zero, and at net zero, then hopefully temperatures will stabilize. if they stabilize, are there going to be major regional variations so that some areas will be hotter, some, you've spoken a little bit about this.
Absolutely. I mean, we talk about global temperature, not because global temperature is a particularly physically relevant quantity. It's just that the global temperature doesn't vary very much due to natural, you see, I mean, the temperature in Oxford varies from one day to the next, just due to natural kind of weather fluctuations.
It's always sunny here, you know.
Always sunny.
Just for our web audience.
Okay, if you say so, Charles. And obviously, the bigger the scale you go to, the more those temperature fluctuations due to sort of weather events become smaller and smaller. And on the global scale, they're smallest of all. So, you know, from trying to sort of separate the signal from the noise, the climate change signal from the weather noise, the global scale is the best scale to go to. But if you actually want to know what's going to happen to you here in Oxford or, you know, anywhere else, you obviously need to know what the weather's doing, like how climate change affects the weather in your region. And there, for sure, the temperatures will vary. I mean, if you live near the ocean, it probably will vary less because the ocean can take up a lot of heat. If you're sitting in the middle of a big continental landmass, it's going to be much greater. But as I keep saying, you know, temperature is not the only thing to worry about. It's how rainfall changes, it's how the storms change, it's how sea level changes. So temperature is not the only thing to worry about, sadly.
And we have a last question from the audience.
Yeah, thank you. You mentioned geoengineering and spraying sulfates into the atmosphere and what that might do to the hydrological cycle. But of course, we have been putting loads of sulfates into the atmosphere. And I was thinking about this the other day about how the MARPOL Convention has 2 years ago stopped something like 70% of the sulfates from shipping. And I'm working on a zero carbon aviation project when on all the zero carbon fuels would either reduce or eliminate sulfates again. Are we going to have a big problem because that takes away one of the cooling aspects? I mean, it saves a few tens of thousands of people's lives as well. But
are we sorry, I missed the last point. Are we going to have problems?
Well, these sulfates that are in the fuels have a cooling effect.
Yes.
And in order to get rid of CO2 and to save people's lives because of the health effects, we want to get rid of, but we end up getting rid of the sulfates. But we don't really know the magnitude of the cooling effect. Certainly in aviation, it's extremely uncertain.
I mean, that is correct to say as we have cleaned up the atmosphere, we are actually making the climate change signal bigger as a result of that. But I mean, the geoengineering issue is sticking it right up into the stratosphere where it will be long-lived. I think the best kind of guides are big volcanic eruptions as to what, you know, effect that would have on the climate system, except that, you know, volcanoes tend to dissipate over a couple of years. So if you're trying to look at long-term things like long-term impacts on monsoons and moisture supply into rainforests, I'm not sure that we can necessarily deduce what's going to happen from existing data.
Do you know if there's any evidence as to what has changed in the last 2 years? Is there any measurable?
The last 2 years?
Since they massively reduced.
Oh, you mean because of the COVID lockdown?
No,
Oh.
I mean because of the reduction of high sulfur fuels and shipping.
I think the effect is, I'm not aware of any sort of measurable effect. I think it's pretty small indeed.
I'm afraid,
you know, that's why, just to say, I mean, just what, I know you're finishing, but just to say that's why, you know, if this geoengineering proposal ever happened, I don't know, we'd be flying, you know, mega flights into the stratosphere and probably military aircraft. 24 hours a day, it would be a continuous process. It's pretty horrible to think about it, really.
Tim, just before we finished, I did want to give you the opportunity for you to talk about your lockdown project. while the rest of us have been learning how to do sourdough bread and things like that, you've been far more ambitious and have written a book.
Yeah, well, you know, like a lot of physicists, I'm in great awe of the great Richard Feynman, theoretical physicist from the last century. And there's a biography of Feynman by a guy called James Glick, who actually wrote a really good book about chaos back in the late 80s, I think it was. And I came across this fantastic quote about Feynman. So Glick says, Feynman believed in the primacy of doubt, not as a blemish on our ability to know, but as the essence of knowing. So that inspired me to write a book about the science of uncertainty across a range of fields, from weather and climate, even sort of economics, pandemics, quantum mechanics. It's kind of a bit of a core dump of my brain over the last, you know, how many years, 40, 50 years or so, I've been doing research on aspects of the climate, of the science of uncertainty. And it's kind of been written as a popular science book. It'll come out later this year. So it's called The Primacy of Doubt, as I say, inspired by that Feynman quote. And if you really want to know, you asked me this question about what my proposal is for quantum mechanics, which we kind of glossed over. You can read it in the book when it comes out.
So I've had the privilege of reading it in manuscript, and I can thoroughly recommend it. So order now. Let me thank the audience, both in person and online, for some really interesting questions. But let me particularly thank Tim. And Tim, we've only touched on your many talents. We haven't got onto you as a rock star. And I do advise you to look at YouTube, where there's some very interesting videos there. Tim, thank you so much for such a fascinating talk and for explaining complex things in such an intelligible way.
Thank you,
Please
Charles.
join me.